how we can solve some simple differential equations, because it's extremely hard to solve every single differential equation. So first we will try to learn the simple techniques. We will also try to understand how we can model some physical phenomena in terms of differential equations. And so that way you will see what is the significance of them, and when we cannot solve them, what are the means we have, so that we can see the solution behavior and what do we mean by solution and those kind of questions. So it will be very applicable course, requires all the fundamentals which we have learned so far. So far as the name suggests, differential equation. So before getting into this term of differential equation, I think we should focus on understanding what is an equation, right? So what is an equation? So let me ask you a quick question here. If I write down here x plus 2y greater than equals to 5, is it an equation? So 2x plus 2y bigger than equals to 5, is it an equation? Okay, so all of you are thinking, like most of you are thinking, majority of you are thinking it's an equation. Okay, so what is the difference between this and this? So first one is not an equation, first one is an inequality. And second one is an equation. So we are learning in this course differential equations. So first of all, it has to be an equation, and secondly, this equation will involve derivatives of one or more dependent variables with respect to one or more independent variables will be called as differential equations. So now, what do these two terms mean here, dependent variables and independent variables? So they are the key terms here. It is greater than or equals to. So this is an inequality. Equation has to be strictly equal to. There is nothing less than or equals to sign in an equation. Okay? Right then? So this is an equation. So what is the independent variable and what is the dependent variable? And we are talking about the equation containing derivatives. So independent variable is a variable with respect to which unknown function is differentiated. So now you would be saying she threw up more terms here. She threw up here unknown function and independent variable again. So independent variable is a variable with respect to which unknown function is differentiated. So I am missing here word which. So let's see, if I have this example right up here, what is my unknown function in this example. Now this is an equation because it has equals to sign. It involves derivatives and it has two variables, as you can see, y and x floating around, right? So what is the unknown function? Y. What is the independent variable? Independent variable is x. Very good, guys. So independent variable is a variable with respect to which unknown function is differentiated. So unknown function here will become y of x. That's the unknown function. And here independent variable is x. So this we got it now from the for the first example. How about the second one? What's the unknown function here? Unknown function in this is what? Unknown function. X. Very good. X. So the script should not, the variables up should not confuse you at all. So you can see in the first equation x was independent variable. By the second it became an unknown function. And what's the independent variable in the second one? T. There you go. Very good. Very good. So independent variable is t here. And unknown function is x of t. Now the second one, the third equation, we have independent variable is what in the third example? Independent variable. S and T. There you go. S and T is an independent variable. An unknown function will be, or dependent variable will be v of s comma t. So v is basically a function of s and t, and independent variables are s and t. So you got the idea how to figure out independent variable and how to figure out dependent variable and unknown function. So basically unknown function or dependent variable is same. So dependent variable here is same as unknown function. Because function also depends, will change as the word variable, it changes its value, and unknown function also changes its value as x gets changed. So what did we learn here so far? Only the definition of differential equation. And in the last one also you can just throw your answers in the chat box. What do you think will be independent and what do you think would be a dependent? There you go. So this is how you will figure it out. Now, after having this information with us, we have to x, y, z are independent. Let me write it down so that we have in notes also. And v of x, y, z is dependent variable. Now, this is very interesting. The last equation 4 is very, very interesting equation. So if we see this equation, we first of all understood that v is a dependent function and x is. But what exactly physically this equation is doing? Or what is this double derivative of v if I take with respect to x and y and z and add all of them and equals to 0, what does it mean? So there is a name for this. So whenever people try to model the diffusion process. That's exactly right. Partial derivatives, very good. And second, partial derivatives, but this is an kind of like I would say in an easier word, operator or a machinery or something like that which operates on this V and causes diffusion. So this thing right up here, this is also equivalent to writing a triangle, if you see back up. And you can Google it and also learn more about this process is called as diffusion. This is diffusion operator. So suppose if you drop a ink in the glass of water, it doesn't really diffuses. It takes a different track of motion. But suppose you think of a heat, like heat traveling, or that's right, exactly. Del is the operator, but this gives you as a particle moves in all different directions. Then V is basically a position of a particle, and if you are in 3 dimensions, then X, Y, Z will determine the location of this V. And saying this is equals to 0 is we are basically modeling a diffusion process. And there's more into it, but I just wanted to give you a feel of it that there is a lot going on in differential equation. Okay, so is the triangle delta? Well, del is this thing, you call this as del. You call this as, it just depends. Some people call it delta, not like Delta Airlines, but delta, and some also, the delta thing is coming when you type in a mathematical software LaTeX, then you can write delta there. So audio is breaking. Okay. If you should be on a very good connection. That's true. That's very good comment that it has to be a good connection. Okay, so I think you would be, when it comes to, it cannot be mine because I am on ESQ server right now. So I am in the department. So I'm not sharing the screen with my local network. So it should not be, this connection cannot be that slow. So you can maybe check once yours, or maybe there is something else. Okay, so what is the independent variable? Independent, we have already discussed it. So what happens, the natural question arises, when we have 2 or more independent variable or more than 1 independent variable, is there a spatial name for those equations? And when we have only 1, what is the difference? So if you have only one or more dependent variable, so a differential equation involving ordinary derivative of 1 or more dependent variables with respect to single independent variable, it is called ODE. So in the previous example which we did above, What are the ODEs? Single independent variable. So let me go up. Which has single independent variable? 1 and 2. So these are ODEs. What about 3 and 4? 3 and 4 are PDE, partial differential equations. They are partial differential equations, they are ordinary differential equations because they have more independent variables in them, and that's what this definition says. If you have more than one independent variable, it is called PDE. Course is all about ODE, but you should know at least a difference between ODE and PDE. And but from now onwards, we will only focus on ODEs. So this we figured it out. Okay, so now let's move on. So are you ready for Popper? Are you all ready for Popper? Everyone is ready? So far, whatever I have discussed in the lecture, that's what you would be using to answer the Popper. Okay. So I will give you a password and I will write it down in a chat box, and you will use that password. How does it work? Okay, so let's first explain that quickly. So when you go to the Blackboard, you click on week 1, okay? You click on week 1 Wednesday session. You click on day 1 Popper 1. Now the moment you will click here, it will ask you, you can click begin. It will ask you a password. So how many of you are till that page that then it is asking for password? How many are till that page? Ready for password? Everyone is ready for password? Okay, very good. So let me give you a password. And you would be getting a certain time to do it. Question will be posed in front of you. And you just have to think a little bit and put your answer. So there is a question in front of you, and here is the password I'm typing in the chat. So just give me a moment. Just 1 second. There you go. This is your password, and this is the problem. Question is right in front on the screen. So keep your screen. The question is right on the screen. So you would see the question. Don't see the question on the discussion on there. See the question shared on the screen. No, the thing is, website did phrase the question. It doesn't have a feature of putting a latex in Blackboard. So that's the reason from next question onwards, you will see that question will be shared by instructor. So, so I didn't deleted that part. So you have to classify, you have to tell independent and dependent variables, and you just save and submit, and you will come to know the moment you did that what is your risk, like whether you got a point, and then you cannot change it anymore. They are in the same model. Because since now you're getting used to the site and everything, so I'm giving you more time. But in future we would be having the reasonable amount of time for the problem, because this is very quick. You can do it in I would say in a minute you can finish this problem. But just making sure that everything is going well at your end. Very good, guys. Very good. So that's how we will first see this. Okay. So now I am changing the setting of that problem, and you will not able to access it anymore. So give me a moment, and okay, good. Okay, very good. Now let's come to the second concept. What is the order of differential equation? Well, I have been doing these sessions in Houston, in University of Houston. I was a clinical assistant professor before coming here. And I was doing this session from during my doctorate and during that year of my job for 5 years. So if you guys are experiencing, might be experiencing this first time, but this thing is very helpful for students. That's how we come to know, and you would see in the long race that I am hoping it will be also very beneficial for you as well. So what is the order of a differential equation? Order of a differential equation is the order of the highest order derivative involved in its expression. So when you see this differential equation right here, highest order derivative, and I should say here, what should I say here? Of unknown function. Highest order derivatives of unknown function involved in its expression. So what's the order of this differential equation? There you go, guys. Order is 2. Very good. What about the order of this differential equation, the sixth one? This is also 2. Okay. How about this one, the last one? Four, you say? Okay, I'll take your words. 4. What about this differential equation? Let me give you this one. What is the order of this differential equation? You are saying order is 5. I would say order is what? What is the highest order derivative in this problem? I mean, this is 1. Right here is 1. So you think order is 4. 1, 2. I would say order of this equation, differential equation, is 1. Because only unknown function is we have first order derivative involved of unknown function. So the order of this differential equation is 1. Okay. So it's not 4. But it's good that you are doing some kind of calculation right up here. And this calculation will be useful in the next concept. Now, after the order, what is the next classification of a differential equation? It's very important to understand when we call them linear and when can we call them non-linear. So how we can differentiate between them, whether it's linear or non-linear. When somebody tells you a linearity or a linear, something is linear, what comes in your mind first? Very good, Ellen. Very good, Daniel. That's exactly right. That's what should come in your mind. No powers, no curves, no x squared, no parabolas. It's a line. That's exactly right. So when it comes linearity, line should come in your mind first. Now, how will you relate this idea of a line with the differential equation being linear? So this requires some thought. And why is line called as linear? That's the first thing to think. Why the line was called linear? Because as you said just now, no powers. As Demo so says, no powers. That made it linear. Why no powers made it linear? The thing is, if you have a line segment this much, and you have a line segment this much, and when you are adding up to make a big line segment here, the addition of the pieces are done back to back, linear. So like x, if you write 3x plus, so say if you write 3x plus 3y, and if you write 3 times x plus y, so why is this same as this? Because I took 3 out, right? I just took 3 out in it, but if we think little more into this, if you have a times x square, say, and we don't call this function as linear, right? We don't call this function as linear. Why? Because suppose if I try to compute here 2 plus 3, that will give me, evaluation will give me 2 plus 3 whole square, right? But if I try to do what? If I try to do y of 2 plus y of 3, it will give me 2 square plus 3 square by the definition of this function. So this is equals to 25 and this is equals to how much? This is equals to 13, and they are not equal at all, right? They are not equal at all. So what I did here, so when the two pieces were added and the function was applied, it didn't behave properly in terms of linearity. So this is not linear function, that's it. But if you had say y of x is equals to x, then if you do y of 2 plus 3, it is 2 plus 3, and if you do y of 2 plus y of 3, it is still as 2 plus 3. So it's not disturbing the structure if you add the pieces before or if you add the pieces. Exactly, linear conformity, that's right. If you add the pieces before or if you split the value, if you add the values afterwards. So it's same. So same thing we have to understand in differential equations as well. Differential equations are said to be linear if this function f is a linear function of variables. When I say f is a linear function of variables, what do I mean by that is f putting it up together. So f is said to be linear if you grab two unknown function y and say y is one function and that we might, what is the best notation? Y hat, say. Y hat is another function. So if you have two functions y and y hat, then f of t y y prime y double prime if you have, and if you have f of t y hat prime y hat double prime. Now what does it mean? What does this mean? What does these two equations mean? Y prime, if I plug it here, and y hat prime y double hat prime y hat prime, what does it mean? What are y and y hat? What are y and y hat? Y and y hat are unknown functions, independent variable, dependent variable. Y and y hat are dependent variable. That's right. They are dependent variable and they both are trying to satisfy same differential equation, right? They both are trying to satisfy same differential equation. So linearity says if I add them both, what will happen if they behave like this? That means they are satisfying the differential equation. Now this is satisfying differential, this is equal to 0. This is satisfying differential equation, this is 0. So that means this has to be also equal to 0. So that's how we will say that f is said to be linear. It satisfies the first property. Second property is f when you apply on a scalar ay, like a scalar times a solution is also solution. That's the idea. So y double prime is equals to a times f of t y prime y double prime. So this is that f is said to be linear. So now coming to this, when can you figure out Which differential equation is linear and which is not linear? Which differential equation is linear and which is not linear? So, if I give you y prime plus x is equals to 0, is it linear? And if I give you y prime plus y equals to sine x, is it linear? And if I give you y prime is equals to sine y, is it linear? Okay, so I got a lot of responses, and let's start understanding one by one. Well, this is not linear. This is linear. And this one is not linear. Now, why is this happening? This is not linear because whenever you have y with y prime multiplied, the fashion which is happening above, this thing, the splitting here, plus thing, this will not hold because you cannot put them apart. Another way of looking at it is, you can think this backwards. If you have a y square and if you differentiate y square, what will you get? If you differentiate y square with respect to x, you don't get just 2y. What will you get? With respect to x, you are differentiating. With respect to x, you are differentiating. Okay, so first thing is to understand, is y a constant or is y a function? Everywhere in this course, y will be a function. Function of which variable here? X. If you are differentiating, you have 2y y prime. That's exactly right. Chain rule. 2y dy over dx. Right? So it is exactly the chain rule which you have. So when you see this equation pop up here, this is a derivative of a y square function which exploited the linearity on the first hand. You have a y square sitting here. Whenever you have y square derivative or sine y is what? Sine y is a series, right? You can write down sine y in terms of a series. So that's also not linear. So whenever you have y prime term or sine of y, where y is an unknown function, they are not linear equations. But here you have sine x, and x is an independent variable, so it's okay. That's perfectly fine. If I put x here, it is still linear. At the moment I put y here, it's not. If I put y square here, it's not linear. Okay, so this is like small hints to understand when it is linear and when it is not linear. So degree is another concept. Degree is basically whenever you take a derivative, you see in the equation the highest order derivative, and then you see what is the power of it. So by power I mean raised to the power. This is raised to the power 1. So for this equation, degree is degree of differential equation, degree that is highest order derivative would have. Forget about the second, these lines. Just forget about it right now. Just focus on first 2 lines. Degree of differential equation, degree that its highest order derivative has. So degree is 1 here. Very good. What's the degree here? Degree is 2. Very, very good. What about the degree in this? Okay. This time you forgot to do calculation which you did last time so much. So last time when I asked the order of the differential equation, you said to me, what's the order here of this? Order is 1. Very good. So order is 1. Degree is what? Okay, I agree with you completely. Order is 1. Full vote to that. Degree is, now the second part of the comes into picture. Degree is 4 actually here. Degree is 4. So degree is 4, and that's exactly what the second part is saying now. Let's understand this. If the equation were rationalized and cleared of fraction with regard to all its derivative involved. And that's the reason we will say here degree is 4. Okay, got it? Good to go? Very good. Very, very good. Okay, perfect. So I try to not put all the information just once. Just we will do it slowly. Okay, so now let's do it the next one. Popper time. So ready for Popper 2? Ready for Popper 2? Okay, so let me see. Let me get the password for you. Okay, so password is this. This is the question which you will have as a Popper 2, and give me a moment to get to view the password. The password is, what do you think? Any guesses on password? There you go. No, it was not that one. I was thinking to select your name, each of your name for one day and make it a password. So Jam12 is a password. And now you might be able to guess the next one. Let's see. Oh, yeah, that is right. So, what should we do? We can do one thing. So, I did a typo, right? I did a typo in this, and the typo so how about give me a moment and I will change your answer choice. Just a second. And I will give you more time, no worries. Okay, you can write. So that's what now I'm fixing. Give me a second. I will fix the password. It will take me just a second to do that. Okay. Okay, so well, try with jam 123. Now here you might see A and B same, but in the options there, make sure notice what are the choices there. Notice what are the choices there in the options. The B option is being changed from ODE to this. If jam 1 2 works, try jam 1 2. If jam 1 2 3 works, try 1 2 3. Whichever, but any one of should work. Really? That's very strange. No, it should be changed. It shows here. Oh, this popper got screwed up. No doubt about it. And you know what? What we can do with this popper, you are right. Damn. No, you should not do makeup. You are here. You should do a popper. Let me try one more time. And what in the world I was when I was doing Linearity and Linearity. I'm sorry about this. Never thought this kind of thing can happen. Okay, buddy, let's do one thing now. I have changed in the system this one, and I hope the changes are made with this. If you get it right, you are done, no worries. So, because it's a system glitches. Sometimes when you keep changing over and over and over again during a short period of time, it might take the previous credentials, but the moment you can see one on one, you're correct, that's good to go. Okay, if everybody gets the moment everybody gets this popper in their jalapeno popper. Oh my god, who entered a jalapeno popper? So the moment you get them, then just let me know. We can move ahead. That's exactly right. Frustration was worth 1 point. No, that won't be there. It can be edited. The points can be edited. So that's not a problem. Okay, so we are good. Let's move on now. The most interesting concept is what is the solution of a differential equation? Solution is something which satisfies a differential equation. That we will call a solution. The moment you plug that function, unknown function, if you know that, into a differential equation, that's the solution of a differential equation. So y equals to gx 2 sine x plus 3 cosine x is the explicit solution of this equation, and x square plus y square minus 25 is the implicit solution. Now why I came up with these two words as explicit and implicit? Okay, so okay, so in order to avoid the confusion for all of you, for this problem, you already, those who have got you all have got the point for it, but just for a good understanding of what the answer is, what do you guys think the answer for problem number 2 is? It is a third order. Is it a linear or is it a non-linear equation? It's a linear equation because we are multiplying y with sine x. The moment I have put here y square, it will become non-linear, right? So this is first is the right answer. That's exactly right. A is the right answer first. Okay. Okay. So now coming to here, solution is something which satisfies. So if I plug back this function into a differential equation, so let's see what I'll do. 2 sine x plus 3 cosine x double derivative plus 2 sine x plus 3 cosine x should be equals to, let's see what this equals to. So if you differentiate this thing, 2 sine x double derivative, what you get? 2 cosine and then negative 2 sine x, right? I just did it quickly. Sine goes to cosine and then cosine goes to negative sine. So sine goes to negative sine and then cosine. So are you all with me with the double derivative of this? Are you okay with this double derivative? Just a double derivative, nothing else I did here. And then I will add the second part as well. So what happens? 2 sine x ticks off with this, and this goes with this, and this is equals to 0. So indeed this is a solution of this differential equation. Right? Cancels out. Very good. Now explicit because we can express y explicitly in terms of x. Here let's see. we are given a solution of a differential equation, how we will figure out that this is a solution of this differential equation? We cannot solve, can you solve y in terms of x here? Well, you would put up square roots and all that stuff, right? Right, you put square root and all that stuff, but to be honest with you, you would not capture, but by the way, what is the geometric interpretation of this equation right here? What does geometrically look like? A circle? Very good. What's the radius? Radius 5. Okay. So this is a circle with a radius 5. There you go. So now, if I try to differentiate this equation right away here with respect to x, what will I get? Let's do it. Differentiate 12 with respect to x. So I should get here 2x plus 2y dy over dx, chain rule. What is the derivative of 25 with respect to x? 0 plus 0 is equals to 0. Okay, let's simplify this. This implies x plus y prime is 0. Ooh, we already got the equation which we have right up here, right? So this did worked out. If we differentiate this, we got a differential equation. So instead of checking, solving for y and this, we did this. Why didn't I solve for y and plugged it here instead of doing this? That's it, right? It's not linear. So you think it's faster? Indeed, it is faster. And what else? That's more work. Okay. There is one very important piece hidden here. When you solve for y, what is the graph of this? What is the graph of this? Half circle, very good. Half circle is the graph of this. And what is the graph of this? Full circle, right? It's a full circle. So when you are explicitly trying to make it explicit, you are not capturing the entire solution of a problem, of a differential equation. Entire solution of this differential equation is a circle, full circle. But the moment you consider only plus part or a minus part, what you are doing is you are considering upper portion of a circle, just upper half, or a lower portion. You are not capturing the entire solution of a differential equation. So this is not a right approach, not giving you full solution. Solution is a circle. So whenever you get an implicit equation, the best way to figure out whether that is a solution of a differential equation, you straight away start differentiating it from scratch. So, so this is a technique you will adopt for implicit solutions when you see. And now let's see here. Oh, whoa, you have a popper 3 up there. Well, popper 3 is so much tied to what I explained just now. So do you have any question here before we get into popper 3? I think we have to implicit and explicit. Explicit is you can write y in terms of x explicitly. Implicit is you cannot write y in terms of x explicitly. This is implicit because we cannot write. If we try to write, we are not getting the full solution of a problem. So writing explicitly, this is not seen as the circle itself, right? So that's the reason this is implicit solution. You cannot solve y in terms of x explicitly, and that would represent a circle. Okay, and for implicit you always have to differentiate. So very good questions, and that's differentiate the solution from scratch to get back a differential equation. Okay, so let's see now. Copper 3 is right up here, and you have your password for this is this. Now these things cannot tell you the next week password at all, but I mean, you can always try it. So 1 jam 2. So this is the password, and you are given a differential equation which was, you have seen that just now somewhere. Now it is asking which of the following functions solves this differential equation. So they should satisfy this. And you will learn a very interesting thing after this example. After doing this example, you will learn very interesting things. It is 1 jam 2. So this equation solutions has a nice feature. They have a nice form. They are a class of certain geometrical family. So you would say, well, this is such a one differential equation, and this solution is so many. I don't want to get to the word, but because that will give you the answer. Why, when you differentiate, do the coefficient disappear from the solution? Because it's equals to 0. You divide it, clear them up. There you go. That's right. Because it's equals to 0, and then you divide by that coefficient. Right? So all the circles are the solution of this equation. How can I figure out which circle is what I want? I mean, I am in the realm of all circles, right? So that gives rise to a very new concept, that if you tell me where I want to start, it will help me. If all the circles are centered at origin and they satisfy this differential equation, then how can I figure out which circle I am on. So if you tell me you are at y at certain point is say 4, that means at 0 you are here, so when you try to solve this, then this specific circle will be the solution of this differential equation, and this both together will form an initial value problem. Given solution, the only way is whether can you express explicitly. Till you don't have a solution, you cannot figure out explicit and implicit. Seeing a differential equation, you cannot. Once you have a solution, you can see the solution and can say it's explicit or implicit, depending on whether you can solve it or not in terms of x explicitly. That's right. That's exactly what Dustin said. That's what I will. But just seeing a differential equation, you cannot. Mostly, I would say if it is a non-linear equation, you would never get an explicit solution. If it's a non-linear. Okay? Linear might lead you to explicit. Just looking at that's what I was saying. Non-linear will not give you explicit solution. Okay? If it's a non-linear differential equation, it cannot give you a explicit solution because you will have y squared term in it for sure. Okay, now coming to here, whether this is a solution of this, what you will do, you will plug this function back up here and you will check. So x squared plus x double derivative plus x squared plus x single derivative minus 2x squared plus x, and when you do this, you would get here 2x and 2, 1 and 0, 2x plus 1 is the derivative here, minus 2x squared minus 2x, and this gives you what? This cancels out 2x with 2x, and it leaves you 3 minus 2x squared, which is right here. So yes, this is a solution. So that's how you will check. You just plug in the function, differentiate it, the left hand side, just work on the left hand side and try to derive the right hand side. So that's how you will figure out whether or show this is a solution if it's given to you. Now I'm moving forward, as this is a very simple example. What do you think? Is this an explicit solution or implicit solution? If in case it solves this differential equation. If in case. Will that be implicit or will that be explicit? Very good. That would be implicit solution if it solves it. Because of what? What makes it implicit? Log. That's exactly right. Log makes it implicit. And now to do this, I will leave it to you. You have to do, I will put it in the recording. It's not linear. That's right. Very good, Seth. And I will leave it in the recording that the calculation of this as we finish up, because we want to finish the poppers by the time we reach the end of the session. So how about I record this, and the same manner I will record this problem. Here also I am treating this as a solution. It has a constant up here, and every function defined by this is a solution to this. So now you can see, well, you have a constant here, but the moment you reach the differential equation, magically this C disappears. The C just disappears. So, where did it go? Well, like y here. Okay, so you differentiate it, and how about I record this as well, right? Because it seems that we are running out of time. I will record this as well because I don't want you guys to be here and um, more than the time involved. Okay, so I will discuss this example quickly and the popper will be based on this example, and then we are good to go. Okay, so fx is equals to c e to the power 3x. This is a function, and this is the most important differential equation, I would say, basic, which you should know after getting out of this class. So when you have y prime equals to y, what is the solution of this differential equation? Y prime equals to y. What is a function whose derivative is itself? Give me a function whose derivative is itself. E to the power x. Right? E to the power x is the only function whose derivative is itself. So, what happens if I start shoving in the constants in front of y? So how does this change happen? What will happen in the solution if I start inserting a constant in front of y? Here e to the power x is a solution. You are very right. This is the only solution for this problem. But can I say this is also a solution? Y prime equals to y. Is 3 times e to the power x is also a solution of y prime equals to y? Yes. So, the family of solution of this equation is, there are a lot of solutions, right? There are a lot of solutions. And for this one, let's see what will be the solution. So when I have, so let me get out from here, keep it separate, this discussion, and jump up to here, y prime equals to 3y. So dy over dx is equals to 3y. dy, you have already done this, over 3y is dx. Integrate both the sides. What I am doing right now is solving this differential equation. But if you don't want to solve this differential equation, what you can do is, you can start with c e to the power 3x prime. This is equals to 3c e to the power 3x, because c is a constant, which is equals to what? 3y. If y is c e to the power 3x, y prime is c e to the power 3x prime, c e to the power 3x and 3y. So y prime equals to 3y is a differential equation whose solution is y equals to c e to the power 3x. So what happens is, whatever comes up here, let me put it in a blue box, blue circle, whatever comes up here comes above the exponential, right? That's what is happening. This thing comes up here and the constant becomes a solution. So this is a solution for this. This is a solution because here is 1. That's why e to the power x it becomes. Here you have 3, so e to the power 3x. Here you have 2, e to the power 2x. And like this it goes on. So let's do the last proper. solutions are possible for the following differential equation? Y prime equals to y. No, it should not be 3x e to the power x. It's a constant, right? Exponential function 3x derivative is 3, Dustin. Right? Right. How many solutions are possible for this? Oh, you need a password, right? Right. That's the password. It's a very easy problem. You can do it in a second. How many solutions are possible for the following differential equation? Only one, no, infinitely many, none of the above. I have already told in the previous example that given a differential equation like this, how many solutions you have? That's right, it's proper 4, that's right. Maybe you can do, you can write down this problem and you have options already in there. Let me show you the problem number 5. But well, for problem number 5, I need to tell you something. I think we close at this one. Problem number 5, if you earn 60% above, you already have done it because we ran short of time. Next time onwards, I will be a little fast and you now have understood how the entire system works. So I don't have to spend too much time. So I will be little going over to it quickly and giving you the thing. So we will stop at topic 4 only. And thank you all for joining me. I will post the recording. I will do some problems more and I will post this recording. You're most welcome. And always you can just take a snapshot of problems and email me and I can do it in the spare session. You're most welcome. I'm so glad you found it helpful. Yeah, sure. I would be online and I will be recording problems. So if you have questions, you can come by in the session and we can work out those problems as well. It's optional, but I will be there. You can make use of snipping tool and take a snapshot of a problem and then email me and I can record that problem for you. Snipping tool, that's like when you go on the rightmost here, here you see a snipping tool, there is my snipping tool. No, yeah, in snipping, when you take a snipping tool is, why my this shield is not coming up? Okay, let me see, now it will come. So when you click on the start here, you should able to see in your computer snipping tool. And I will write it down here. Snipping. Right. I see. Windows has snipping, Mac has that. Okay. That, yeah. I always use Windows. Mac is like virus free, but yeah, that this is exactly what I was saying. So when you capture your problem, whichever you're doing, you just email the picture of that. You can do it with the phone also, I mean, whichever way you like. And in the web work, the problems which you're working on, or in the textbook, wherever you think is interesting and you need to know something, so you can always just Okay? Okay, very good. You're most welcome. Bye-bye. Okay, so let me start now recording the remaining questions which I have. So for this differential equation, if you would like to solve, this is an implicit and we can differentiate step by step here. So logarithm function y is a function of x. So 1 over y dy over dx by chain rule, we will get a derivative of that, plus by quotient rule we can differentiate this numerator, derivative of denominator minus, so well it would be good to go other way around because minus sign should come here, so let's do this way. So denominator derivative of numerator is 1 minus numerator derivative of denominator divided by the square. That's the quotient rule. You will get this differentiation. Derivative of a constant is 0, so this is equals to 0. Now if we simplify this, we will get, we multiply throughout by y square. We get y dy over dx plus y minus x dy over dx is equals to 0. Now we can, we would like to get this differential equation back from here if this is a solution. So we can collect the first and the last term, bring them together. So y minus x dy over dx plus y is equals to 0. And that's exactly the differential equation which we have on the top. So that's how you would be able to get for the implicit solution, a differential equation. Now coming to this one, we have a function y and we would like to see whether this is the solution of this differential equation. We will differentiate this one. So differentiating this function, I can apply product rule to this because I have two functions here. So g of x cubed plus c e to the power minus 3x divided by dx plus c times x cubed plus c e to the power minus 3x. Now this differentiation of this entire thing we can do by product rule, x cubed plus c, and derivative of this is negative c e to the power negative 3x plus e to the power negative 3x square. Now we will add the last term which we have. We get x cubed plus c e to the power minus 3x. So let's just simplify this expression. We will get here negative 3x cubed e to the power minus 3x negative 3c e to the power minus 3x plus 3x square e to the power minus 3x plus 3x cubed e to the power minus 3x plus 3c e to the power minus 3x. So, examining all the terms here, we can see that this term and this term cancels each other, and the same way this term and this term, the last term, cancels each other. So we are left with 3x squared e to the power minus 3x, which is exactly equals to the right hand side up at the top. So the function fx equals to x cubed plus c e to the power minus 3x satisfies the differential equation y prime plus 3y equals to this. So that's how you will solve. So yes, it satisfies the differential equation. DE, differential equation. Now, as we discussed this example already in the class, now seeing this, it should y prime equals to y has infinitely many solutions because y equals to c e to the power x is a solution. So like this, we have infinitely many solutions for this problem. Any constant we change, we will get a solution of this problem. Now, what did we learn in this example back up here? Let me go up. We learned that if we consider y square plus x square equals to constant, for every value of c, this is the solution of this differential equation. But how we will figure out that which circle we want to be on? So for that we need extra condition to get a unique solution. So basically we are getting here family of solutions. In order to get a unique solution, we need extra conditions. Now, how can we figure out those extra conditions? Differential equation, we need extra to get unique. Is there any connection of that information to the order of differential equation? And answer is yes. There is a connection of that information with the order of differential equation. So, I'm skipping this slide, and that gets me to this one saying, if I have a differential equation, I will need how many initial conditions depending on the order. If the order of differential equation is 3, we need 3 initial conditions. If it's 2, we need 2, and if it's 1, we need only 1. So depending on order, we will need the initial condition. And we will start from here on Wednesday, on Friday.